I would like to try to keep this talk kind of non-confidential. This stuff was research I did before Google, before I joined Google. And also, actually, this is going to be published kind of soon. We're trying to submit on transactional information systems. So I will ask you not to say things that are Google-related or whatever, because we are trying to put this on YouTube or Google Talk series, whatever, public stuff. So if there are questions that are related to Google, maybe we can keep that for the end when we stop recording. So Google doesn't endorse, maybe doesn't even like this kind of work. As I told you, this stuff is public, but still maybe you didn't see them yet. So I don't know. That's why I'm here. So I will present this work I did on how to use collection selection on a search engine architecture. And actually, slides are available online here. The URL is kind of easy to remember. OK, the motivation is what you expect. So the web is growing, and more than that, it's changing the way it's used. So people are expecting good information, reliable information, and they expect to have results fast. The index is growing, and also the data that's stored in the index is growing. You know, there are more quality signals that are used in when indexing, ranking, and finding pages in the web. And a parallel architecture is probably the only way to manage this thing. There is no big machine that can hold just the index in one chunk. There are several research, and parallel architecture are the only way to do it. There are billions of pages that are stored today in index, and there is a need for partitioning this data into manageable chunks. So a parallel architecture, a parallel information retrieval system architecture is what you probably know. There is a front end that collects the query from the users, and underneath there are a bunch of servers that are keeping a part of the index. And each index is queried, and the results are merged and sent back to the user. So this is a common, simple architecture. But the problem is over here. So we have an index. In an information retrieval system, the index is a data structure that matches documents with terms. So every time a term appears in a web page, we put a little X here, and we have a big matrix at the logic level. That's showing how terms are appearing in various documents. And in literature, there are two main ways to split this up into several chunks. One is split them horizontally. So one server is responsible for a set of terms. And the other one is this one, where one server is responsible for a set of documents and knows about all the terms in these documents here. So if you have this architecture, every time you get a new query, you're going to contact all the servers that are holding the terms. So if this server is holding terms that are not in your query, this will not be working. In this architecture, you're going to probably broadcast the query to all the servers, and every server will tell you which documents are matching your terms. So this is the basic idea. There are different advantages and problems with these architectures. So as I told you, if you split the terms, only the server with relevant terms will be involved in answering a query. And this can bring to reduce the computing load of the overall system. But actually, there are problems of load balancing, because some terms could be more popular or more queried or whatever, more complex to answer. Also, if you go into details, there is an heavier communication pattern between servers in a term partitioned architectures, because you've got to exchange the posting list, and it's more costly. I won't go into detail anyway. The document partition has better balancing, but as I told you, all documents are queried, so all servers are involved into the query. And we would like to try to see a way to reduce the computing load with an architecture that's document partitioned. So that's the goal of this research. The main architecture, the overall architecture is structured like this. There is an interface that does caching and collection selection. We will see this into details. And on the back end, you still have your search cores. You're collecting statistic data, but the core is here. We perform a collection selection. So every time we get a new query, we choose which servers are going to be queried for the specific request. Okay, so the main contributions of this research are the three that are listed here. So the document model is new, is different, and we represent a document not with the terms that appear into the document, but by the queries that are able to recall the document. And this is actually a better representation and allows for more efficient partitioning and selection. Also, there is this new concept of load-driven routing. So when the query is sent to the servers, we also consider their instant load at the moment. And we base our decision on this information. And then there is this new thing that's called incremental caching that, differently from a basic cache that just improves the throughput, it's also able to improve the result quality. OK, I need to acknowledge my co-authors and all the reviewers that contributed to this work. OK. Other contributions that probably I won't have time to show today are a more compact collection representation. This is more compact than the state-of-the-art CORI, and it's actually outperforming its results. Also, there is a new way to find documents that are contributing only to a tiny fraction of the results. So about half the collection, as in our experiment, has low-quality results, and we could just send them to another supplemental index set of servers or something like that. And also introduce a new way to update the index, so to add new documents to the index. And a contribution actually is relevant in the academic field, not at Google, is that actually the test set was quite big for the standard. So it was 6 million documents and 2 million queries. It's nothing like things we're treating at Google, but still. OK, so first of all, let's speak on how to improve the partitions. So how to split documents into servers so we are able to offer a better service to users. So we have a document collection, and we need a partition strategy to map the documents onto several servers. And one strategy is just to do a kind of random assignment and then broadcast the query to each server. So just to have load balancing, we spread the documents all over randomly or round-robin fashion with no control. And every time we get a new query, we just broadcast it to all servers. There are other strategies like doing document clustering based on the content or the links or stuff like that. But in this talk, I would like to show you how to use past usage, so information from the query logs, to do clustering, to do document clustering. And the way it works is as follows. So you have a set of training queries, and those can be, I don't know, the top queries from your query log or a sample or whatever. And you record every time which documents are matching which queries. So let's say query 1 is recording document 1, 4, 8, 10, and 12, and so on. And so you've got all documents here. In my case, it was 6 million. You've got all your training queries. In my case, it was about 200,000. And then you perform co-clustering. So OK, document J is returned by the query. And co-clustering is a very robust and fast algorithm that sorts columns and rows into blocks like this. So the co-clustering is trying to aggregate ones and zeros in blocks. And you have a cluster matrix that can be seen as 3 by 3. You've got 3 document clusters and 3 query clusters. So every time we have a new query clusters, we just concatenate the queries together, and we call this query dictionary. And this will be used later for collection selection. While the document clusters are set 1 per server. So every server will hold 1 of the clusters. So the co-clustering is a very stable algorithm. I told you was presented in literature about 4 years ago, and is able to find the clustering that minimizes the loss of information between the original matrix and the cluster matrix. So it has a very strong theoretical basis. The implementation can scale up because it's prone to be parallelized very well. And it's very robust because you can change the test period. You can change the number of clusters. You can change also the matrix model. I won't spend time on this. But across all these changes, the results are consistent. So it's very, very, very reliable. The way we use this for collection selection is that when we get a new query, we compare it against the query dictionaries we created, and we can rank the query clusters. And then we use the result of the co-clustering to choose the document cluster. So we have a rank of each cluster. And I will show you this in more detail in a second. So let's say this is the result of our co-clustering process. This is the sum of the scores that appears in the rows and columns contributing to this little block here. So you're summing the contribution of each document in this cluster and each query from this cluster. You sum it here, you have a matrix. Every time you get a new query queue, you do just a search of the query against the dictionaries, against the query clusters. So imagine that you have, in this case, 3 query clusters, and each of them is described by the concatenation of the queries. And you look for the query into this set of concatenations. You do, random. You do usually information retrieval stuff like TF-EDF or OCAPI25, all standard things. Anyway, you get a rank. You're able to rank your query collections, and then you do column by matrix, and you're able to rank the document collections, and you can order them. So let's say that the third document collection is more promising than the other ones. So you can sort them, and you say, this is the first, this is the second, and so on. What you do now is that you start querying the servers in that order. So every time you get a query, you start querying first the most promising server, and then so on. We did some experiment to verify what was the quality of the results we could find using a subset of servers, such as the most promising. The experiment was on a set of about 6 million documents, and we use about 200,000 queries for training, and we use about 800,000 queries for tests. So this represented 3 weeks. So compare with Google. This represented 3 weeks of queries in 2003 to this small search engine called, I didn't write it, TotalBR, whatever. So anyway, this represented this represented a real sample of queries to a small search engine. And we tested with queries from the subsequent weeks. These are unique queries, and these are also repeated queries. So this is why it's so smaller. The documents were split into 16 document clusters, and we created 128 query clusters. And we measured the intersection, that is the number of results we could find in a subset of servers with respect to the full index. And also we used this more complex matrix that actually was not just measuring the intersection, but the value, so the score of the results. But I mean, these gave similar results. This is some mathematics that describe better the quality matrix. But I mean, the intersection is just this is the metric for intersection. So we intersect the results we get from our server set with the ground truth. Okay, whatever, that's simple. Anyway, let's look at the result 1 second. So we tried different partitioning and different selection strategies. And the first one was just to use CORI, that's a standard collection selection architecture, on a situation where documents were randomly assigned to documents. So if we just do collection selection, we try to query the first server, the one that's believed to be most promising, we get, let's say, 0.3 documents out of 5. That if you do mathematics, it's just 1/17. It's just random stuff. So collection selection is not helping you if you have random assignment. While if you do the co-clustering as I just showed you and use CORI on the same thing, you're able to have a big improvement of about 5 times. So if you partition your documents beforehand and you use CORI, you're able to get about 1/3 of the documents that you will get from the full index, but just on one server out of 16. The 17th server in our experiment was just the set of documents that were never recalled in training. So all the documents that queries couldn't find ever during the training were set over here. And these are our, if you want, supplemental index, and didn't contribute much to the result. So if you look at the main set of documents, using just one of over 16 servers, you get 1/3 of the results. So, and you can choose your point, you can choose your quality by increasing the number of servers. If you use our new collection selection strategy, you can go about 10% better than CORI. So this is actually outperforming the state of the art. And this represents what happens. So if you choose to use only one server or 2 servers or whatever for each query, you select the most promising and you query just 1, 2 out of all your set, you have this nice precision curve. So using just one server, you can get about 1/3 of the results you will get from the full collection. And if you want to have, I don't know, 2/3 of the collection, you need to use about half of the servers. But actually, this region is very interesting because this means that if you have a peak load or if you have failures or if you need to accommodate a lot of peak load, you're able to give reasonable results with very, very limited resources. But we can still improve this. Anyway, there are already some very interesting ideas in this point. So when you do the partitioning, the popular queries are driving the distribution. And this is good because actually popular queries will find better results on average. Also, as I told you, we are representing the documents in a new way. It's a lower dimensional space. And actually, it's also better when you're trying to do other type of clustering based on vector space. It's a more efficient collection selection. It's about 1/5 smaller than CORI. And also interesting, you can build this representation while answering other queries. So the search engine could be running in the meantime, and you keep collecting results. I tried to find out what were the weak points. And one could be that actually there is dependence from the training set, but we changed that and didn't affect the results too much. It's true that we cannot manage terms that we've never seen before. So when we do the training, we concatenate the queries we got from the from the users. So our training set is a limited vocabulary. If you have a new term, you're not able to find it in any query cluster. So this is actually a problem. You can go back to CORI. CORI is a technique that uses all terms in the dictionary. It's much bigger for this reason. But actually, if you look at the average, at the aggregate result, it doesn't improve too much. While our incremental cache technique is actually helping a lot in this case. And you will see this in a moment. Also, the collection selection depends from the document assignment you do at the beginning of your configuration. But actually, if you add documents, you don't break performance. And this was tested. OK, so let's see what happens with load distribution. So this strategy has the same drawback of term partitioned architecture. So some servers could be more popular than others. So there can be a big difference in load between one collection and another. Because, for instance, this collection is holding all documents of very popular topics, and this collection is holding not so popular stuff. So there can be a big difference. And actually, this is a cost to the search engine because there is a machine that's underutilized. So what we would like to do is force the load to the same peak level. OK, the load in this case is very approximate measure. It's the number of queries in a sliding window of about 1,000 queries. So this is just approximation. But anyway, if you use this architecture, you're still reducing your peak load from 100% that would be serving all queries to all servers to about 1/4. And with this limited load, you're able to get about 1/3 of the results. So we introduced 2 load balancing strategies. And in simplifying this, the way it works is like that. Every time we get a query and we rank the document clusters for the query, we give a priority to each collection. And the priority goes from 1 for the most promising server down to 0. So it's linear decreasing. And every server chooses to, OK, we broadcast the query. And every server answers if its load is smaller than its priority times the threshold we set. So when this is 1, so for the most promising server, the server I will always answer. When this is decreasing, the server I will answer only if its priority is only if its load is more than the priority times the load. And there's a little variation that's not important. But anyway, in this configuration, a query gets answered by the most promising servers, the most the one that were ranked highest, and also the servers that are at the moment idle or underutilized. In this configuration, we are modeling the cost as just one. So every time a server is answering a query, we add one, and we count the number of ones. So very simple model, but we're going to work on this, and we're going to improve this in a moment. But anyway, if you look at the result with this little strategy, you're able to push your load from the blue bar to the red and the yellow one. The yellow is the little, the different version that I just skipped quickly. So this is just a snapshot at a certain point of the load that's being held by all servers in the configuration. So if you just take a snapshot of the load of your servers, you're able to, all of them are running to peak power. And actually, the results are improving a lot because this was what we had before when we chose to query, let's say, 4 servers per query. So this is the initial configuration. So let's say we have a query, we find the most promising 4 servers, and we query the top 4. Keeping the same peak load, that's about 1/4 of the 100%. We can get about 10% results better just by using this strategy that's using idle load. So without increasing computing power, this technique is about to improve about 10% of the results. And no, this different version is adding a little more. But at every measure, at every level, we know added computing load, this trick can improve your result significantly. Also, okay, caching is another interesting point. When you do collection select, okay, this is some background. So result caching is used in all web search engines because it's able to prevent popular queries to slow down the servers. So very popular queries are not sent to the backend and are intercepted by the front end and just sending the results back to the user. It's interesting also because when you have caching, it's reshaping the distribution of your queries. And so after caching, not so popular queries become very popular, compared to the full set. Here we introduce a new caching system that's taking care of the collection selection. There is a drawback when you just do caching with this strategy. So if you have a query and you do collection selection, maybe only 1 or 2 servers are actually answering your query. So if you cache, you're caching only a part of the result. And if you're serving this information back to the user will find the graded result. So what we try to do with incremental caching is that every time we get the same query, we're going to add new results to the cache. So over time, popular queries will have a full set of results. So this is interesting because repeated queries will have actually the full set of results, and they will see no negative effect of collection selection. Okay, so what's happening now is that the incremental cache is, yes, reducing the load to the backend because it's intercepting a part of the queries, but it's also improving the result quality at the same time. Okay, and this is the new set of results if you add incremental caching to load-driven routing. What happens is that you're able to move from, let's say, 3.5 results over the top 5. You're able to get 4 results out of 5. Using the same load, you would have to guarantee that just 4 servers are queried every time. So I would say that in a different way. If you configure your system so that you're able to query to guarantee at least 4 servers per query, with the same peak load, you're able to get about 4 results out of 5. And this is true more or less with different metrics and different configurations. So if you change the cache size, if you're using a static cache, if you're changing the training week, the test week. Across all different configurations, actually, adding no load, you can get very good results. So before we were using a simple model cost where a query costed just 1, but actually we refined this and we use real timing for the queries. And the results actually were confirmed. So we changed a little the simulation infrastructure. So at this time, the servers determine their own load, measuring, for instance, the computing time to answer a query, and they sum up that over time. And still, they answer if their load is smaller than the priority of the query times their computing power. So again, the broker, so the interface, the front end, is ranking the collections and is giving different priorities to each collection for the query. So it's broadcasting the query to all the servers with a tagged priority, and each server will choose to answer if the instant load is smaller than the priority times the peak load. And so if the priority is 1 for the most relevant server, this will always answer. And for less relevant servers, they will answer only if they are idle or underutilized. And actually, it's important to choose a cost that's not simply 1, because the cost varies a lot, from milliseconds to seconds. So this was actually on, in the machine at my university, there were other applications running, all that stuff. But still, this was a gross approximation. Anyway, so we actually partitioned the documents onto different servers. Every server had the local index. So every server was able to answer queries for the documents it was holding. And we measured the timing of each query. So actually, the real timing was used to compute the load and drive the system. There was a little change here. So before we measured the peak load of the system, and that was our I'm sorry, that was our threshold for dropping queries. But actually, if you take the sum, the peak is very high. So actually, we did the average load. I mean, this is a small correction. But anyway, the results were confirmed. So actually, we're confirmed that actually are even better, because if you're using collection selection, what is this one? Yeah. So if you're using the load-driven strategy and collection selection, you're able to guarantee about 2/3 of the results you will get from the full index. By using the computing load, that's guaranteeing you just the first most authoritative server. So if you are able to tune your system so that at least one server is guaranteed to be able to answer to the query, using the idle load and the caching, you're able to get about 2/3 of the results with no added computing pressure. I also did some results on a bigger load, query logs. This is actually 2 million queries, and results are more or less confirmed. OK, so this concludes. This was pretty fast, so there is time for questions. In this work, I tried to present an architecture that's using heavily collection selection. So documents are partitioned onto several servers, and only a set of servers is used to answer. This load-driven strategy with the incremental caching can get actually very high result and reducing heavily the computing pressure on the system. And it was verified with different simulations and different configurations. So the way it's going to be used is like this. If you're trying to reach a given precision, you can use fewer servers. And if you're given a limited number of servers, you can get better precision. And this was confirmed with different metrics. This actually is showing how to, this showing a trade-off between cost and quality. And it's boosting the focus on top results at the expenses of low-quality results. But it can be useful if you're serving a very big collection of data and you can afford to lose some results. Also, this can be interesting because the load-driven routing can be used dynamically. So if there is a peak load or if some machines are failing or whatever, you can use this strategy to reduce the computing load to accommodate more users, more queries. Another interesting thing is that still, even if you're using collection selection and you're using servers independently, there are ways to have consistent ranking. So when you get results and you merge them out of the servers, the results are actually consistent with what you would get with a full centralized index. And at the end, I was telling you briefly before, the incremental caching is actually good also to reduce the negative effects of selection. So if you have terms you've never seen before, and you're not able to do a good collection selection, but if that query is for some reason popular, so there is a new term that becomes suddenly popular, like, I don't know, iPhone or whatever. What's new today? Anyway, so if you have something new and everybody's asking about that, the query will get populated and you will get full correct results also for the new term. There are other things that are very interesting. You know, there are very good applications. There are some more potential. There is some more potential also. If you're doing posting list on the local index,
sorry, what's a posting list?
The posting list is the line in the. If you have your document and term metrics, the posting list is the line. So it's the line that for every term gives you all the documents, more or less. So if you're caching terms on the local index, you will get somewhat more focused queries because only queries that are relevant to that server will get there. And so actually the cache will have less, you know, there will be less noise for the cache, for the local cache in the server. Also, there is a way to add new documents that's not breaking performance. So there is a way to add documents to the collection without breaking the performance. And actually, it's very important because you want to be sure that when the collections are changing, your collection selection function is still working well. And at the end, there are ways you can improve the caching, not just by using, I don't know, list recently used algorithms, LRU algorithms for the cache. But for instance, you could use information based on query frequency, or maybe the number of servers you already polled. So if you have a cache line that's fat because you've queried a lot of servers, maybe you want to keep that over time instead of swapping it out. And that concludes. I've got some backup slides if there are questions on the training, on adding documents. And otherwise, we can just call it a day. Thanks for coming. Hey.